So my plan was to spend 3-4 lectures discussing the basic models for the transmission of infectious diseases. So we talked about motivation. Last lecture, we spent most of the time understanding, proving simple theorems, but theorems about the SIR model for a directly transmitted infectious disease. And then we talked about the public health implications. I'm almost done. I need maybe 5 more minutes, and then we move on. Then today, I want to extend this basic model first by adding natural births and deaths, and then by letting the transmission rate be time dependent. So we all know that we get sick more in the winter than the summer, right? We get the flu, we get cold viruses more in the winter than in the summer. So we want to put that into the model. I think today I'll get to talk about measles, and now you can begin to understand what I mean by we have a new method, and this is a very new method, to obtain the time-dependent transmission rate, beta of t, from given I of t. So it's kind of an inverse problem, but we'll talk about that. And again, it's embarrassingly simple. And then probably not today, but probably tomorrow, we talk about modeling indirectly transmitted infectious diseases. So this is the model that we've been talking about. I proved what's called the threshold theorem. So we defined what I call the most important quantity in epidemiology, R naught, the basic reproductive rate, which is defined, well, this is the definition using the model. And I just stressed that this involves F0. So this is a number which is determined at the beginning of the outbreak. You can let R be time dependent and let defined R of t to be S of t beta over nu. That makes sense. Actually, that makes a lot of sense, but when people talk about R naught, it's at time 0. So the big theorem is that R naught is a threshold. If R naught is less than or equal to 1, then the infection decreases monotonically to 0. And if R naught is bigger than 1, then you have an epidemic. So the number of infected starts increasing, but we know that it reaches a maximum, and then it decreases to 0 monotonically. And these are plots of representative solutions. Then we talked about how many people are still susceptible at the end of the outbreak. So how many people got sick, essentially? Because we know that I infinity is 0, right? And we have an expression, a very nice transcendental expression for the percentage of people still susceptible. So the percentage of people who did not get sick at the end of the outbreak as a function of just R naught. And this was the plot. Okay, quiz time. So a student here asked me an excellent question. Dengue, as I mentioned last lecture, sorry, has an R naught of about 3. So if you look at this plot, that would say that maybe 90% of the population has been infected with dengue. Right? If you believe this? Do you believe that? Now, from what I understand, most cases of dengue are very minor. You may not know that you've been confronted with dengue. You might have symptoms of like a mild flu. I'm sorry?
And are not reported.
And are not reported, yes. So I mentioned that one of my projects with some people at the CDC is studying Shigella, which is a diarrheal disease. Usually very young children get it in preschools. And one of the questions they want to know is how underreported it is. And our estimates are about 100 to 1. I think I'm going to show you tomorrow some data, some World Health Organization statistics for cholera. And the question there, an interesting statistical question, is how underreported is that? You know, is it 100 to 1, 1,000 to 1, and so on? So this is my question, and think about it. I won't tell you the answer yet. But the doctor will take blood at the end of the lecture from everyone. Okay, so we originally defined the R0 using parameters and initial conditions in the model, but then our interpretation is that R0 is the number of new infections the number of secondary infections caused by each primary infection at the beginning of the epidemic. And I stress that this is the definition you find in all epidemiology books, and it's independent of the model. Okay, and these are some representative examples. As I mentioned, the estimates for H1N1 is essentially 1.3. Now, that is also space dependent. So I have some colleagues, some biostatistician colleagues at Emory University who are essentially trying to put R0 on a map and study sort of the spatial distribution of R0. But for an average, it seems to be about 1.3. And then we talked about how to prevent an epidemic. You prevent an epidemic by making R0 less than 1, and you have all these parameters that you can try to, reduce, or in the case of nu, to maximize. Okay, then we talked about vaccines. So vaccines move individuals from the susceptible class to the removed class. And the question is, not everybody can be vaccinated. So do you even try? So is it possible to prevent an epidemic, meaning make R0 less than 1, by vaccinating only some subset of the population? And if you can, what is that population? I mean, what is that subset? What does it depend on? And we have the technology to do a trivial calculation, which is just this. So what we get is that if 1 minus 1 over R0% of the population gets vaccinated, then R0 is less than 1, and there can be no epidemic. So for R0, well, we talked about this. I don't want to go through this again. Evolutionary biologists will tell you that they believe that pathogens evolve. We all know the pathogens evolve, right? Some extremely fast, like many influenzas, some much slower. But they'll all tell you that pathogens evolve to increase their R0. So they evolve to become more easily transmitted and to make individuals sick longer. Okay. So let me just review. So we've seen that there are 3 fundamental roles of R0. So R0 is a threshold value, meaning R0 bigger than 1, you have an epidemic. And again, I claim that this is a great use of mathematical modeling, that this is very difficult, if not impossible, to detect from, say, data. The second application was that the percentage of susceptibles at the end of the epidemic is the root of this expression involving just R0. And then we just saw that the critical vaccination threshold for herd immunity is 1 minus 1 over R0. Okay, so R0 obviously is an extremely important quantity, but I tried to give you some indication last lecture that it doesn't explain everything. So how do you estimate R0 from data? So I'm going to present, I guess, 3 ways today, but let me start with this. So starting with this little transcendental equation for the number of infectives at the end of the outbreak, you obtain this. In fact, it should be, oh, that's, what did I do here? No, that's right, okay. So if you assume that at the beginning of the outbreak, there's just a small number of infectives, okay? Then what that expression says is that R naught is approximately equal to this expression. So how can you estimate S infinity and S zero? At least for some diseases, you can look at blood. So if you have blood taken from random, if you have blood samples taken from random individuals, like in a city, so say in an emergency room or something like that, you can test for antibodies, for instance. So if you have older blood, you can test for antibodies, and that, you know, if you have a large enough sample of blood, then that would let you estimate S0. And then after the outbreak, if you have a representative sample of blood, you test for antibodies, and that will give you S infinity. So that's one way in which epidemiologists try to estimate R naught. There are less painful ways, but okay, so let me say something very quickly about a stochastic version of the SIR model. So one defines a stochastic version, again, this is the simplest way of doing it, as a continuous Markov process where time is continuous, but what do you call them? The values that it attains are positive integers, 0, 1, 2, 3, and so on. So we have S of t, I of t, random variables for all time, and the process is given by sort of axioms 1 and 2. So an infection corresponds to a transition from Si to S minus 1, I plus 1. Right? So if somebody becomes infected, you have one less susceptible in the population and one more infected, of course. And the stipulation is that occurs at rate beta times Si. And removal corresponds to the transition from Si to Si minus 1. And that occurs at rate nu times I. So this defines a continuous Markov process. And then you can apply what you know about Markov processes. So in particular, like it follows from this that during their infectious period, an infected individual has contacts with other individuals determined by a Poisson process with rate beta. And it also follows that how long an individual is sick, is infected, well, that's now a random variable, of course. And it's a random variable with an exponential distribution. So we all know that the expected value of an exponential random variable is, with parameter nu, is 1 over nu. Right? So for the stochastic model, the expected period of infection, how long, the expected value that an individual is sick for is 1 over nu. Right? Which agrees with what we saw for the deterministic model. So if you do simulations, and it's easy to do simulations, people usually use the Gillespie algorithm, which I think I mentioned in the notes. Here's a simulation. So obviously red is the number of infectives, black is the number of susceptibles, right? And green is the number of removes. And you see that these curves, again, this is for a single run, you know, look like reasonable approximations to what we saw for the output of the deterministic model. Okay, so now I want to add demography, or I want to add vital rates to the basic SIR model. So I want to now consider natural births and natural deaths. because if you're studying something like dengue or something which is going to occur over a long time scale, you have to include this. Okay, so we're going to assume that newborns enter the susceptible class with no immunity. Now, for many infectious diseases, newborns inherit immunity from their moms, and you can add that later. But the second most basic model, we assume that newborns enter the susceptible class with no immunity, and we're going to assume that in each component, the S component, the I component, the R component, you have a natural death rate, mu. And we're also going to assume that the births occur at a rate n. Now, for now, you could think of this as n of t, the total population size. Remember, for the previous model, I showed you that n is constant. A priori, that's going to be true here, but a priori, it's not obvious. So we think of this as n of t, the total population size, meaning s of t plus I of t plus R of t times mu. So schematically, this is the picture. And if you ask why this, well, this because this is going to make the total population size constant. If that's not realistic, it's easy to modify. But again, I want to stick to the basics. Okay, so this is the new system. Obviously very similar to the old system, except we have this term, we have this term, we have this term, the natural births, we have the natural death term for the susceptible class, the natural death term for the infected class, and the natural death term for the removed class. Now, if you add the three left-hand sides together, you get how the total population is changing in time. And if you add the three right-hand sides together, and you think for about 2 seconds, you get 0. Because n of t mu is equal to, well, n of t is equal to s of t plus I of t plus R of t. So we just proved that for this extended model, the total population size is conserved, is constant. Okay. What is the duration of infection? So before it was 1 over nu, it's the rate at which infectives become removed. So what is that rate? It's nu plus mu now. Right? That's the coefficient of I. So the period of infection, the duration of infection now is different. It's 1 over mu plus nu. So it's smaller. And that's because some infected people die a natural death while they're in the infected class. So this is very natural. So we define a new R naught, which is this. And the theorem is this. And this, I want to spend some time proving this. So the theorem is if R naught is less than 1, then the number of infectives decreases to 0 as t goes to infinity. Infection dies out. So in other words, the equilibrium point corresponding to everyone susceptible, no one infected, no one removed, I'm going to prove is globally attracting. If R naught is bigger than 1, there are 2 equilibrium points. One is at everyone susceptible, no one infected, no one removed. And that's a saddle, so you're not going to see that. And the second one is what it is. And I wrote it down in terms of R naught. So the first is a saddle, and the second is attracting, locally attracting. And I claim that if you start off with a positive number of infectives at time 0, then this equilibrium point, the second one, is globally attracting. So for all initial conditions with I of 0 positive, then the number of infectives will approach this number, this non-zero number, as t goes to infinity. So in particular, if R naught is bigger than 1, this leads to endemic disease. Over the long term, there are going to be sick people, this many sick people. And if R naught is equal to 1, you're essentially in case 1. So unlike the basic SIR model, the disease doesn't die out, right? Before I infinity was equal to 0, now it's not true. Now, of course, we can recover everything for the SIR model from this model by letting mu be equal to 0. So we see if mu is equal to 0, then I of t goes to 0. Okay, so again, I want to spend a little bit of time proving this. One important component of the proof is linear stability analysis. So I prepared a couple of slides for students. So this is certainly one of the most important concepts, one of the most important tools in ODEs. It might be the most important one. Okay, at first I wrote the most important one, but then I backed down a little bit. But it's certainly one of the most important concepts. And the idea, I mean, it's an absolutely great idea, is that you want to understand the stability, or compute the stability type for an equilibrium point for a nonlinear differential equation. You reduce the question to the stability type for an equilibrium point for a linear differential equation, and then you solve that problem using linear algebra. Okay, so patience. I don't have that much patience. Come on. Here we go. So the big theorem, sort of the super theorem, maybe the ultimate theorem in linear stability analysis is the Hartman-Grobman theorem. So let me state it carefully. So let me also state it generally. So you have an autonomous system, x dot is equal to f of x, nonlinear system, and you have an equilibrium point x0. So you consider the linearized system, which is u dot is equal to the Jacobian matrix of f at the equilibrium point times u. Right? You can write down, at least in principle, the solution explicitly for the linearized equation. It's just in terms of matrix exponentials. So this is the solution to the linear equation. So with Hartman-Grobman, I'm sorry, one more thing. The linear equation has the origin as an equilibrium point. So what Hartman-Grobman tells you is, assuming all of this, and assuming that no eigenvalue of the Jacobian matrix is 0, and no eigenvalue is pure imaginary. So if that says if the equilibrium point is so-called hyperbolic, then there's a homeomorphism from a neighborhood of the equilibrium point 0 from a neighborhood of 0 thought of as the equilibrium point for the linearized system to a neighborhood of x naught thought of as the equilibrium point for the nonlinear system, such that h takes trajectories, or if you like, parametrized orbits for the linear system to the nonlinear system. So orbits usually are non-parametrized curves, but this is stronger. This is saying that the parametrized orbits, trajectories, I'm not even sure in English how to say this, get taken by h to parametrized orbits for the nonlinear system in a neighborhood of the equilibrium point. Okay, so what this says is that the orbit structure or in the neighborhood of a hyperbolic equilibrium point for the nonlinear system is topologically the same. That's what a homeomorphism does for you. As the orbit structure near the equilibrium point 0 for the linear system. So as a consequence, they have the same stability type. If one is an attracting spiral, the other is an attracting spiral, and so on. So the stability of the equilibrium point for the nonlinear system is the same as the stability for the equilibrium point 0 for the linear system. Okay, so let's prove theorem 3. So we have two equilibrium points. Okay, I write it as N0 and S star I star. And again, I do that because since the total population size is constant, I don't have to write the third one. Okay, so we compute the two Jacobians. You just do it, and that's what you get. So let's concentrate first on the, if you like, the trivial equilibrium point at n 0, 0. Okay? What are the eigenvalues? Well, this is a triangular matrix, so you just read off the eigenvalues from the diagonal entries. So one eigenvalue is minus mu, and the other eigenvalue is this, which you can rewrite just using the definition of R naught as this. Now, we're assuming first that R naught is less than 1. So this quantity is negative. So we have two negative eigenvalues. Okay, so using linear stability analysis, using Hartman-Grobman, we know that the corresponding equilibrium point is attracting, at least locally attracting, right? Okay, so now I want to claim that it's globally attracting. So how can I claim that it's globally attracting? So first, I want to use the Poincare-Bendixson theorem, and the next slide is a description of the Poincare-Bendixson theorem. But I want to show that there are no limit cycles. How do you show there are no limit cycles? Well, limit cycles are global objects. You can't use linear stability analysis to detect that. But I claim that if you know, and there are different ways of seeing this, if you know that every limit cycle must contain an equilibrium point. So that's a consequence of Poincare-Bendixson, index theory, and so on. It's a non-trivial fact to prove. But just believe that. Okay? Well, we have one equilibrium point, right? Here's S. Here's I. We have one equilibrium point at N 0. So if we have a limit cycle, it has to contain this equilibrium point. So it has to look something like this. Well, we're assuming that R naught, I'm sorry, look at the... Right. Wait, hold on, I'm sorry. No, the other one doesn't exist if R naught is less than 1. Wait. Hold on. Oh, the other one is a boundary. Yeah, right. Right. Anything wrong here? Well, down here, that corresponds to negative infectives. Right? So that can't happen. Okay. Can you have homoclinic or heteroclinic connections? Well, this is attracting, right? Can't happen. They have to be saddle points. So I claim it follows immediately from the Poincare-Bendixson theorem that this equilibrium point is globally attracting. Also, before I remind you of Poincare-Bendixson, if R naught is bigger than 1, then you have one eigenvalue negative, you have the other eigenvalue positive. And again, by Hartman-Grobman, so you have a linear saddle, and Hartman-Grobman tells you that you have a nonlinear saddle. Okay, so Poincare-Bendixson, it's a theorem about systems in the plane, so it's strictly two-dimensional. Okay, and I'm not stating it precisely, you know, I'm more or less precisely, but I'm trying to give you the intuition if you don't know it. So suppose you have such any autonomous system like this, and I'm assuming everything is smooth, and you have an orbit, and you have an orbit which is, say, bounded in positive time. So for all t bigger or equal to 0, it stays in some compact region. And the question is, what does the orbit look like? What can the orbit be? So in particular, what can the orbit accumulate on? If you like, what's its omega limit set? And Poincare-Bendixson gives you a complete list, and it's a very short list. So what Poincare-Bendixson tells you is your orbit could be an equilibrium point, or it might accumulate onto an equilibrium point. And, you know, an attracting node, spiral, so on. It could be a limit cycle, or it could accumulate onto a limit cycle, or it could be a heteroclinic or homoclinic connection, or it could accumulate onto a heteroclinic or homoclinic connection. And that's it. Okay, so we have an orbit, we have a single attracting equilibrium point, we know there are no limit cycles, we know there are no heteroclinic or homoclinic connections. So that tells us that our, at least locally attracting equilibrium point has to be globally attracting. I'm getting some strange looks. Okay, I need one more result, which is very useful in low dimensions, and I just need it in 2 dimensions, which is where it's completely trivial. And it's what's called the Roth-Hurwitz theorem. So suppose you have a 2x2 matrix, and this is its characteristic equation. Okay? And I'm interested, what I want, I have differential equations and stability in mind, so I want to know what are conditions on A1 and A2 to ensure that the eigenvalues have negative real part. And the condition is simply, or the conditions are simply A1 positive and A2 positive imply that the 2 eigenvalues have negative real part. Okay, this is a very simple exercise in dimension 2. Okay, there are various versions, more complicated versions in higher dimensions. It's still useful in dimension 3, but then it becomes much harder to apply in higher dimensions. Okay, so let's go back to the proof. So now we're studying the second matrix, or I'm sorry, the second equilibrium point, so-called endemic equilibrium point. And we write down the characteristic equation. And the characteristic equation is of this form, x squared plus a1x plus a2, where a1 is this and a2 is this. Now we're interested when R0 is positive, right? So when R0 is positive, it's just obvious that A1 and A2 are both positive. So now we apply the Roth-Hurwitz theorem. And that tells us that both eigenvalues for the Jacobian matrix have negative real parts. Now I apply Hartman-Grobman to tell me that the endemic equilibrium point for the nonlinear system is locally attracting. Is that clear? So now I want to argue that it's globally attracting. So how do I prove that it's globally attracting? Well, let me use Lyapunov functions, a global Lyapunov function. So again, let me remind you briefly what the idea is. This technique works in arbitrary dimensions, not just 2 dimensions. Okay, let me stress, it's very important for Poincare to be 2 dimensions. It's false in higher dimensions. But this method works in any number of dimensions. So, of course, I illustrated for a system in the plane where I'm going to use it. So you have an equilibrium point, and suppose you have just a single equilibrium point. And we don't even need to know that it's locally attracting. You just have some equilibrium, you have a unique equilibrium point. And suppose that there exists a smooth function defined on the plane such that it's 0 at your equilibrium point, it's positive everywhere else, and it goes to infinity as x and y go to infinity. So you think that you have a bowl, so the graph of V is like some bowl, right? Which its minimum is at the equilibrium point, and then it just gets bigger and bigger as you go farther out. And now the key condition. Suppose that for any initial condition, any orbit, which is not the equilibrium point, V strictly decreases along the orbit. Okay, so again, I want this function V to be strictly decreasing along every orbit. So how do you ensure that? Well, you ensure that by showing that for any orbit, the derivative of V along the orbit is negative. And the theorem is if you have such a V, then that equilibrium point is globally attracting. Okay, and the proof is, it's very geometric. You start with an initial condition on the graph of V, and what's going to happen? Well, property 4 tells you that this point is moving down V, keeps moving down V. If it stops before getting to the equilibrium point, you easily argue that where it stops is another equilibrium point. But we're assuming a unique equilibrium point. So it has to keep going, it has to keep going. V has to keep getting smaller, smaller, so it approaches the equilibrium point. And you turn that into a proof. Okay, so I claim that for our SIR model with demography, this is a global Lyapunov function. Now, to be a little bit precise, I stated this theorem for systems in the plane. I need to really restrict to systems in the first quadrant, but that's fine. That's fine. So this function L is a global Lyapunov function, and it's very easy to check because you just use the chain rule and you use the differential equation. So at first you might think it's impossible to check, but it's actually pretty easy to check. Not pretty, very easy to check, that this is a global Lyapunov function. So this proves, or at least this is one way of proving, that the endemic equilibrium point is globally attracting. At least all initial conditions in the open first quadrant. Okay, so we have this equilibrium point, which we know is, we call it globally attracting. So it could be a node, or it could be a spiral. If it's a spiral, then we have oscillation. So let's study that case a little bit. So, and it could be either, depending on parameters. So that the endemic equilibrium point will be a spiral if the discriminant of the Jacobian matrix is negative. And you just write down the discriminant. It's just simple algebra. It's this. And if this quantity that I call delta is negative, then the endemic equilibrium point is a spiral, which says that the solutions oscillate to the endemic value. So this is a representative plot of this is S of t and this is I of t. Right? So S of t is oscillating to its equilibrium value, and the same thing for I. Now, if you put in realistic parameters for measles, so let's go back to this slide, which I essentially showed you last lecture. So this is actual data from England, or from the UK, I should say, from 1948 to 58. And it's the number of infectives that's actually reported every week, but I think aggregated to every month, but that doesn't matter. But what you notice is something kind of striking. You see oscillation with a 2-year period. That's kind of obvious. And you don't need to do a fast Fourier transform to spectrogram, whatever, to do this. I mean, that's completely obvious. Okay, so let's go back to our model. So these plots were actually done with initial condition, with parameters from measles in the pre-vaccination era in the United Kingdom. And what it shows is oscillation. That's good. It gets the period correct. So with realistic parameters, the oscillation period is about 2 years. On the other hand, clearly, these oscillations are decaying. But in the UK, they didn't decay. So by adding demography to the basic model, we've recovered the periodicity, or we've obtained the periodicity. We have the right period. But somehow something is missing in the model to sustain the oscillation. Okay, so what's missing from the model? And I'll come back to that in a few minutes. But before I do that, let me mention 2 more ways to compute or to estimate R naught in real life. So one way is, let's go back to the theorem. We always estimate R naught in the field by going back to our theorems. Come on. One more. So S star is mu plus nu over beta, which is essentially, what is it, R naught over S naught. Or is it S naught over R naught? One of those two. Okay. Okay, so if one assumes that essentially everybody is susceptible at the beginning of the outbreak, okay, and again, this is assumption which may or may not be true, but if one assumes that that's true, then in this model, R naught is equal to the total population size divided by the number of susceptibles over the long term. So it's 1 over the proportion of susceptibles over the long term. And again, using collected blood from a representative sample, this is something which can be estimated and is estimated. I mean, this is certainly one of the ways of which epidemiologists estimate R naught. And then let me skip 4. Let me keep going. Okay, so I want to start extending the model. Okay, and again, my goal is to, well, I want to extend it by adding an exposed class. And then, once I do this, the model that we obtain is what I call the workhorse model. So if you look at any recent paper on modeling infectious diseases and they use differential equation models, they're essentially going to start with this model. So I'm essentially taking you to the state of the art for ODE models. Okay, and then for various, especially viral diseases, researchers allow the transmission rate beta of t to be time dependent. So I'll come to that. But first, let's talk about adding a so-called exposed class. So remember, the SIR model, or SIR with demography, assumes that as soon as you become infected, you become infectious. You're able to transmit the disease. But for many infectious diseases, that's not true. That it takes days, maybe a week. For HIV, it's even longer than that, to become infectious. So for many diseases, investigators add a so-called exposed class, an E class. So again, those people are infected, but they're not yet able to transmit the disease. So schematically, this is the picture. So again, we assume that we have natural deaths in each of the 4 classes at rate mu. We assume that we have births at a rate n times mu. And we assume that beta is the rate at which susceptibles become exposed. Alpha is the rate at which exposed become infected. And nu is the rate at which the infected become removed. Okay, so this really covers a lot, right? So we have natural births, we have natural deaths, we have disease-related deaths, and we have these 4 classes. So this is the system. So now it's 4 equations. And again, if you add the 4 left-hand sides, you get how the total population size is changing. If you add the 4 right-hand sides, you get 0. So again, the total population size is conserved. If one defines R naught in this more complicated way, so the number of susceptibles at time 0, beta, alpha, over this, then one proves the following theorem. If R naught is less than 1, the disease dies out. If R naught is bigger than 1, there are 2 equilibrium points. One corresponds to nobody, to everybody susceptible. The other one is endemic disease. And furthermore, if you start off with a positive number of infected, then over time the number of infected approaches this positive number. You now have all the techniques you need to prove this. Okay, the proof is very similar to the proof of theorem 3. So I'm not going to repeat the proof. Okay, I didn't use Poincare-Bendixson to prove theorem 3 because it doesn't work here. That's why I used the Lyapunov function, and you can write down a very similar looking Lyapunov function in this case. Okay, now those who are very observant will notice that I of t in this model approaches this number, which is the same number you've seen on a previous slide for theorem 3. You just have to compare. Okay? At first it may look like there's no need to add this extra class, this extra E class, because the long-term dynamics are the same. But it's a little bit more subtle than that. Epidemiologists will argue that this E class is very important because even though over the long term the number of endemic cases is the same, that the growth is slower if you have the exposed class. And that makes perfect sense because the growth of number of infected is slower because individuals need to spend time passing through the exposed class. And well, again, although it doesn't sound like this makes a big difference, it really does in a number of models, especially for viral diseases. Okay, so maybe I have three, four minutes. let me at least begin by introducing a time-dependent transmission rate. Okay, so again, as I said before, for all of us know that we get sick more often in the winter than in the summer. And it's well known that for childhood viral diseases, and again, think pre-vaccination, mumps, rubella, chickenpox, and so on, children contact these diseases far more often during the school year than during the summer holiday, and actually during sort of Christmas vacation, Easter vacation. So what a number of researchers have done, and when I'm telling you, I think much of this has been done in the last 5 years, so this is pretty recent. What they've done is they've tried to include, they let beta of t be time dependent depending on the school year. And again, think childhood viral diseases. That's what we want to model. So you let beta of t be time dependent, and you let it be kind of small during summer vacation and during Christmas break and so on, and you let it be higher, maybe much higher, there are some actual estimates, during the school year. Actually, this is a good place to stop. So let me just stop here, and I'll start tomorrow's lecture with this. Thank you.